Good reaction.
No, I'm just looking at someone's work for rate predictions. Hello, word. Oh my.
All right, welcome everyone to lecture 9. So this is the second to last full lecture of Info 1998. And then we have one more workshop right after. So quick question before we actually get too far into the lecture is, can we get a progress update on the final project from people? Raise your hand if you haven't done anything for the final project. Okay, that makes me feel really good. So that means that we have a decent amount of progress. So if you have any questions, then feel free to drop by after the lecture, and I will be sure to help out. And I think the deadline is probably online, right? Does anyone know the deadline? Okay, I think it's the last week of April, but let me double check that. I don't want it to go into like dead week or finals week, so we'll have it at the last week of April. But of course, you can budget your time starting from now and make use of the extra time you'll have, hopefully after the second round of prelims are over, to maybe plan a little better, but make sure to let me know if I can help. So today's lecture is about unsupervised learning and clustering. This is kind of like a new paradigm of ML for us. So we've talked about, supervised learning before, and unsupervised learning is, it's the opposite of that, but it turns out that unsupervised learning is more respectful of what data is like out there in the real world. And let me talk a bit more about why that's the case. So far we've seen supervised learning. So in supervised learning, we feed in data, and that data we said has what? Anyone? Starts with an L. Yes, I heard it. Labels. Yep. So we say that the data is labeled, right? So labeled means that, if we're trying to model something, we have some kind of target, and we have data where we in fact know that that target has been achieved or that it has not been achieved, right? And that's a very useful characteristic because then we can go and take the loss and compute the difference between what we ended up predicting and what was actually supposed to be predicted. And then, we're able to then use gradient descent or a bunch of other algorithms to optimize our weights and fix a model. But how often in the real world, let's say you're working with a huge data set, right? We're talking not millions, but billions of data points. Can we annotate all those data points with accurate labels? Probably not, right? Oftentimes we really can't. And so we need ways to be able to look at inherent structures within our data. Instead, those inherent structures themselves actually speak to the tasks that we are trying to accomplish. So it becomes very different now when we're talking about unsupervised learning. And when, this is a bit of a digression, but models like ChatGPT, they make use of both. So they will do not unsupervised, but something we call self-supervised, semi-supervised learning, where you feed in unstructured data and have it learn a lot of relationships based off of that. And then you will do the final kind of fine-tuning steps with supervised learning. So you will have labeled data for that. So you often use a mix of both in practice, but to get to the scale that we've achieved with ChatGPT, we need unsupervised techniques. So that's why it's very important to know. And we're kind of stepping out of the very protective world that is supervised learning. So far, we've learned a handful of supervised learning techniques, and this is a bit of a quiz. So tell me which of these are regression models and which of these are classifiers. So first up is k-nearest neighbors. Raise your hand if you think it's a classifier. All right, raise your hand if you think it's a regression model. Cool, so classifier. What about linear regression? Classifier? Oh, almost got someone. Regression? All right, everyone, cool. Logistic regression. Classifier? Who's raising their hand? Be proud, loud and proud. There we go. Thank you. Yes, it is a classifier. It is the most stupidly named model in the world. It is actually a classification model. It's a binary classification model. Whoever named this model honestly did not think at all before they did. So remember we did this last lecture and it actually comes up with a decision boundary. So it is actually a classifier. Perceptron slash SVM, no more tricks going forward. So is this a classifier? Raise your hand if you think so. Cool, yes. And decision trees slash random forest. Raise your hand if you think it's a classifier. Raise your hand if you think it's a regression model. You're all right, thank you. Good, Noah, right? Good job. Oh, or was that a question?
I'm Logan.
Oh, Logan, sorry, Logan. Okay, cool, thank you, Logan. That was correct. So yes, we can have random forest models. There's classification and regression trees or CART. So those algorithms can do both. But yeah, so that is the supervised learning kind of domain. But now we want to talk about the limitations of this. So I already said, right, like we need labeling. But to put that in perspective on why that's so challenging, just imagine, right? Like there's image segmentation tasks out there. So that means that let's say you have an image of farm animals. You want to bound out the cows in an image, or the pigs in an image, or the chickens in an image. But what if you make small mistakes, right? And just imagine like actually going pixel by pixel to trace out every single like plate thing in the image that belongs to like a cat or a dog, right? It's a very time-taking task. And there have been, there's companies like Scale AI. So Scale AI, what they'll do is they will kind of hire people who do that, but they're always focused on the post-training aspect. So once you've trained on a huge amount of data, at that point, they will allow you to kind of fine-tune towards tasks. But to understand whole image domains, we no longer just feed in these labeled images. Instead, we feed in a bunch of data off the internet. There's huge data sets out there that basically just scrape the internet, and then we feed them in as input, and they learn like overarching structures about images, like the things that could come up in images, right? So they just become really good at understanding images in general. And then when we want to kind of tune them towards tasks, we'll then use supervised learning. So whenever we want to achieve scale, we need unsupervised techniques. So that is your takeaway. In terms of, I guess, like modern deep learning, this is kind of how supervised learning plays in. It's at the very end of the pipeline, but the bulk of the work is done by unsupervised models. So like we said, the data in unsupervised models is unlabeled. So take this example right here, right? We have a training set, we have a bunch of people. Let's say we have two features, right? The x-axis is maybe whether, let's say it's like how old they are, right? And then the y-axis is how tall they are. And then maybe we can learn some underlying representations within this data because they form these clusters, right? These little clusterings. Maybe we can learn underlying representations that tell us, their dating profiles or something like that, right? So that's what we're going to talk about is there's structures within the data maybe that we can exploit. Because at the end of the day, it becomes kind of weird when we think of something as an unsupervised task, right? Because before we said, I know exactly what I want to achieve. I know what I want out of my model, and I will guide you towards getting there. But here it's almost like saying you're on your own. It's your job to figure out the structures within the data. And how do we accomplish that, right? So anyone have any ideas they want to float out there for how you think we can accomplish this? Yeah, no worries. So what I touched upon, this idea of clusters is what we're going to chase at first. So there's a bunch of unsupervised learning techniques, by the way. Technically, dimensionality reduction also comes under the umbrella of unsupervised learning, but this is kind of like a feature engineering task, so we don't usually think of it as the modeling tasks. But today we'll only focus on clustering models. So some of the big ones are k-means, hierarchical cluster analysis, Gaussian mixture models, and then one of my favorites is dbScan, which I'll show you visually. It won't be on the slides, but I'll show you a demo for it. So when we're working with clustering, right, our loose definition when we think of clusters is actually a pretty natural one. All we're saying is that clusters have objects which are similar in some way, as well as dissimilar to other clusters. So another thing that we say, and this gets a little deeper, is that clusters are latent variables. Does anyone want to float out a definition of a latent variable? What does latent mean in English, plain English? Yep.
Hidden?
Hidden, that's a good one. Yeah. Hidden, underlying, that's what it means. So the best way to think of latent variables is maybe with a demo. So let's say that someone was only facing this wall right here, right? So they're looking entirely backwards. So if there's someone who's putting up like projections, I can't see my hand. Actually, I can't actually see my hand, but I could see the like shadow of my hand, right? So I know that it's a hand and I know how many fingers I'm holding up or what gesture this is, not by perceiving the actual object, but by perceiving its shadow. So that's what a latent variable is. It's when you're looking at an underlying representation or something that's hidden, but you can observe what is going on. So in that case, which one was the latent variable? Was it the shadow or was it my hand?
Your hand?
Yes, it was my hand because what I was observing was the shadow. But what was, I guess, underlying, which is what I was trying to represent, was my hand. So what we're saying here is that the clusters themselves are maybe these underlying uh, I don't know, maybe we can call them oracles in some sense because they're more intelligent than just, it's like a little feature or variable. Instead, they're like these entities which are broadly like capturing the data, right? So we oftentimes you've used YouTube and you've used social media. You talk about recommendation systems. They rely very heavily on these unsupervised techniques. But at the end of the day, it is actually just clustering. So when we understand clusters, we can yield underlying trends within the data and then use those trends for predictive analysis. So here's a good example of the, I guess, like average clustering task. You'll just often be shown like a huge blob of data, but you can kind of see, right, that maybe there's clusters 1, 2, and 3. So we want algorithms which can give us these. And then when we talk about prediction, what we're saying is, okay, well, we have these clusters. What if I had a brand new point, maybe something out here? Which label should it get? Should it get red, green, or yellow? Right? So that's what we talk about when we're thinking inference time with clustering algorithms. So in this case, you can see that there were no labels here, right? You didn't see any labels. I just gave you a ton of blue points. And I didn't say what they actually correspond to. And it was the algorithm's job to figure out, how many, how many clusters is actually a hyperparameter that we set. But once it knows how many, it's the algorithm's job to actually go and find those clusters. And they won't actually always be this neat, especially in k-means, which I'll show you. They'll oftentimes be very initialization dependent, which poses an issue and which is why you might need to train multiple times. And also because, like I said, you need to set the amount of clusters that you want. So if I said 4, I would have gotten a different thing here. Maybe I would have gotten like another split here, right? So there's a bunch of factors we need to kind of bring in. And that makes sense to me. Why? Because we're losing that very amazing ability to say, I know what this should be, right? Because we used to be supervising. So I know what this should be. So I'll use that information to figure out how wrong my model is and then work backwards from there. That's always what we were doing with supervised techniques. We were always working because we had this very valuable knowledge of the degree of error, right? So we lose that now. So we need to instead focus more on the metrics that we're using, on hyperparameter tuning, on the quality of the algorithm. A lot of different things play in. Before I move on, any questions about this? Okay. So like I said, you guys have all probably used these websites, Google, YouTube, Amazon, Netflix. All of them are going to use recommendation systems, right? And there's a bunch of reasons why they do that. One way in which they'd use it is, people who you are similar to, they'd want to show you similar products to them. And then the other way is, based on the products that you've looked at, what products would you want to look at, right? And the I guess common theme in all of unsupervised learning is this notion of similarity. We always need to exploit similarity, right? So similarity will soon relate to a distance metric. And distance metrics are something we can quantify. And ultimately, that's how we will go about constructing these unsupervised like models, is by using these distance metrics. But we will kind of follow along with this recommendation system example. to put things into perspective. So the first, I guess, type of recommendation system is collaborative filtering, which basically says people similar to you have also liked the same content as you, right? So that means that I can use other people's ratings or judgment of content in order to inform my own content. And this makes sense, right? Like, let's say you're looking online and you're someone who's really interested in um, old, like, piano concertos or something like that, right? If I'm YouTube and I know that there's a bunch of users out there who clicked from like one piano concerto to another, then it makes sense that if someone else is sitting on watching that exact piano concerto at that moment, then I should recommend to them that next piano concerto, right? So I can use that data to my advantage. So it's not supervised because there is no correct answer on what I should show, but there are similarities, and I'm exploiting those similarities across users to come up with recommendations. So pros are that if the cluster behavior is clear, then it's good and it's interpretable. But you can imagine how expensive this is, right? Because let's say it's YouTube and there's like millions upon millions of users. It's pretty hard to look at each of them and figure out, well, which one, should I actually end up with? So I think I have an example on the next slide. Yeah, so we have 5 people. So they watched 5 movies, and minus means that they didn't like it, and plus means that they did like it, right? So why don't we look at this right now and tell me which users seem to be the most similar? There's 2 people who seem to have very similar preferences. Yep.
Send AB.
Chris and Amy, is that right? Okay, that is right, actually. That is very correct. I forgot about that one. There's actually, okay, I lied to you then. There's 2 pairs then. There's another pair of users who are also very similar. Anyone see them? Yep. Sorry, you said Mike and Ken? Yes, yeah. Okay, everyone else was thinking that as well? Cool, yeah. So Mike and Ken. I forgot I made these 2 similar as well, but you can see that like they actually have the exact same list so far. So then I would probably like a good question to ask maybe is like, okay, should I recommend the movie Fargo to Ken? Well, I noticed that he's very similar to Mike. So most of his preferences have been alongside those preferences of Mike, right? So the answer should actually be yes, I should give it a plus, right? So again, this is not how these algorithms work, but visually, I want you guys to kind of confirm for yourselves that it makes sense that I can steal this label basically, right? I can steal the information from Mike and know that it's a good recommendation from Ken because their histories are so similar, because they actually form clusters. If you were to plot these actually, if you were to plot Mike and Ken, they would be the exact same point. So it's more than just a cluster. They're actually lying right on top of each other, right? But you can imagine then, okay, let's say there's one-off differences in different features. Well, that's what creates that variance. And then if they're still similar in other features, that ends up making those clusters. So we have these nice clusters that we can work off of. So this is the collaborative filtering example. But the other thing that we can do is content filtering, which is just kind of isolate you as an entity, right? Like you want to look at content that's similar to what you are currently viewing. So a pretty simple version of that for which you don't need any kind of learning algorithm is like, if you watch the first episode of a TV show, then what should Netflix recommend to you? The second episode of the TV show, right? So that's a very silly case, but you can imagine then like if Netflix looks at your whole history of what you've been watching, and also factors in other things, right? Like the recency or maybe the geographic location. Maybe you watch certain videos more when you're at Cornell, and then when you go back home, you watch other kinds of videos, right? If it starts to factor in those other aspects as well, you can imagine there is this huge like multi-dimensional plot that's out there of the type of content that you're watching across several different features, right? And there's clusters within that, which it then will start to exploit and figure out what point, like it brings in a video and it aligns it with all of those other features and it says, okay, based on this, we should actually show this person this video. right? So that's what we're doing when we say we're doing content filtering. So again, it is intuitive and it is pretty scalable. But I guess an issue is that if you're a brand new user and you have no history, and you could try this right now, you could go and use YouTube signed out. It'll still use something maybe that it has from cookies, but oftentimes it'll be like very boilerplate content, right? Like it'll usually recommend things from the trending, things that are maybe current news, but it won't be anything like what you have when you're signed in. So you need to build up that watch history in order for YouTube to know what to recommend to you. Any questions on this so far? Yeah, it's pretty intuitive. So the meat and potatoes of this lecture is how do we actually perform cluster analysis? So I spoiled it a little before because I told you guys that we actually will use distance metrics to our advantage. So you guys probably know like this equation, right? It's basically just figuring out the distance of 2 points. So the reason that this is useful is because if we look at this across all of our features, we actually have one single number that tells us how close 2 points are. And we can use that to our advantage. So, and by the way, this is a bit of a digression, but there's hierarchical cluster analysis, which we skip over because there are these weird tree methods that you don't ever really use. And we have k-means clustering, which is what we're actually talking about, and Gaussian mixture models, which are a really cool extension of k-means models. So I will talk about the second two today. So the first algorithm is k-means clustering. So we have a little GIF here, which is kind of going through it. But what you do is you pick k centroids. So centroids are what? Does anyone remember from geometry what a centroid is? Yeah, so centroids are like, if you imagine some kind of geometric shape, they are going to be the mean of that shape. So when you're not dealing with like, like maybe a triangle or a square or something like that, then what you're going to have is maybe these messy points, but we can actually compute the centroids of these points as well. And the way we do that is we just take an average of each dimension. We take an average of like, okay, how many points do we have maybe at x equals 1, how many at x equals 2, right? And then you multiply and then you divide out by the amount of points you have in total. And then you do that for each of your dimensions, if that makes sense. So it is a pretty intuitive thing to try out. So we'll start out with k centroids and we'll put them at random places, right? So I can initialize them basically anywhere. And don't worry, I have a good visual after, which we'll walk through step by step. But once I do that, I will go and I will cluster points by calculating the distance to each of these randomly initialized centroids. And then I will assign a given point to the closest one. And then I will look at all of the points which belong to each of the clusters, and I will take their average, and that becomes my new set of centroids. And then I will repeat this process. So who wants to see a demo of that? Because I'm sure that that did not make much sense. Cool. Okay, so let's do a quick demo then of what this actually looks like, and I'll talk through this. And I think I can send you guys this link as well. It is a pretty cool website. So let's say, okay, so here's what I'm doing, right? So we'll pick the initial centroids randomly. So they will be placed randomly anywhere within our grid. And let's say, actually, no. Okay, let's do this, right? So 3 clearly separated centroids. And then I set the k value, right? So what should my k value be here? You can hold it up on your fingers. Yep, I'm seeing 3. So the k value is 3. So let's add 3 centroids. And okay, I don't like that it actually put 2 of the centroids in a good place. But the third one, you can see it is actually random. So the green one ended up like maybe the green one will have to move a decent amount. So what is the first step here? Well, what we'll do is for each of these individual points, we'll compute its distance to each of the centroids, right? So let's look at this point right here. Can you guys see my cursor? So it is this point right here. What we'll do is we'll look at its distance to the green centroid, and then the blue centroid, and then the red centroid. And this like interface is really nice. It's showing us that like the blues area is all of this, and then the greens area is all of this. So we already know which points are going to be the closest. But you can imagine going through and doing that for each of the points that we have, right? So it is going to be a pretty slow algorithm. But once we do that, what is the next step? Well, we will assign the points to those clusters. So you see that they changed colors. So all of the points that are closest to the blue centroid end up getting that blue color, and same for green and same for red. So what's the next step from here? Well, I'm calling these centroids, but if you look at them, is this green point actually the center of all of the green points? No, you're shaking your head no, and you're right. So it is not the centroid right now. So we will update the centroid to actually be the centroid of this clustering, right? So everything that's green will go and will compute the centroid. And by the way, spoiler, the green thing will move to maybe somewhere around here. Red will move to maybe somewhere around here. And blue will stay around where it is right now. So let's go ahead and make that update. And you can see that they shifted. And once they shifted, we now have these lines kind of moved, and that's just the area of influence of that centroid. But we have reassignments to make. So particularly anything that's like blue within a green area, or like green within a red area, all of that needs to now be reassigned to the red cluster in this case, and then the green cluster in this case, right? And what am I actually doing there? Well, I'm just looking at the distance between this and each of the centroids. And I know that the closest centroid for this blue point is actually this green point. So I need to make my reassignment now. So when I click that, I reassign, and now they've turned blue. But are these centroids right now? They are no longer centroids of my new clusters. So I need to make an update. So if I make the update, then they become centroids. And at the very end, there is a little bit of extra work that they do, right? So I can reassign update centroids, but at this point, it's actually converged. So the model has converged here. So who can kind of now make sense of what's going on with this algorithm? Cool. Yeah. So any questions? I have a question for you guys. What happens if the random initialization is different? Will I always end up with the same cluster assignments? Raise your hand if you think yes. Raise your hand if you think no. Cool. Yes, I agree with you. So this algorithm is very unstable and it's very initialization dependent. Let's see if I get lucky and we can get a very bad example. Okay, you know what? Actually, we don't need to get lucky, but I'll just make the bad example. So let's go back. I will choose the centroids, and then we will go back to the Gaussian mixture case. And let's see, I did like something like this, right? Let's see if these actually move. They probably will actually. Oh,
The greens are consistent. All the green clouds. I see this.
okay. So this is a very easy case, right? So obviously this would work, but in some examples, if we add 3 centroids, so they all ended up here, and now let's see what happens. Okay, so I keep getting unlucky. But there are bad cases. I don't want to waste too much time on this, but there are bad cases, and the way that they look is that you might have like the red point like end up somewhere here where it takes half of these and then half of these. So it doesn't actually converge to the clusters which you think of in your head. And the reason that's the case is because we repeat until there's like minimal changes in the amount of in like the point assignments, right? So basically when we're no longer reassigning points, and it can be proved that you can always converge with this algorithm, but what you converge to is not always good. So that is the that is the k-means clustering algorithm for you. I think that it is one of those algorithms which feels not very ML-like because we're not computing losses, we're not doing anything like that. In fact, it seems very iterative and it seems very slow. It seems like something that you could actually write up in a couple of lines of code and with a bunch of while loops. That's totally true. You can. So it is an interesting algorithm, but it does get us pretty far in terms of understanding like how we work with these clusters. So this is a greedy algorithm, like I said, right? So it's always going to take that assignment which it comes up with by figuring out which of the clusters it's closest to for each of the points. And when we initialize randomly, that's going to oftentimes lead to like suboptimal cases. So one way to get around that is to maybe try multiple different initializations and go with the one which is giving you the best test time performance. And also we have a major dependence on the value of k. So I have another question for you. What if I have as many k value have as many centroids as I have data points? So let's say I have n data points, and then I also have n centroids. So in this case right here, we're imagining that I had a centroid for every single data point that I had. What should happen? Usually. It's a pretty deep question. This comes up in the ML class as well. So any ideas would actually be pretty cool. If anyone wants to float something out there, don't be shy. Yeah, go ahead.
So the centroids end up with no points in their like.
I see. Okay, so that is a good point. So you are making the point about what happens with the centroids and the points. And I like that. I'm gonna table that for a second and see what Sean had to say.
The majority of points, they're all going to get their own centroid.
Yes, so that is a little closer. So what Sean says is that all of the points, it's actually all of the points, they should get their own centroid, right? So because I initialized n centroids and I have n points. Imagine n equals 3, right? And you have 3 centroids and 3 points. Then each of the centroids will end up exactly on top of the points in the data set. That'll give me a training error of 0. So by increasing the number of centroids that I have, I can actually always decrease my loss. So that's an issue because it's misleading. If you're trying to figure out the best value of k, it becomes misleading as to where that happens because it's always going to decrease as you increase the value of k. Does everyone see why that's an issue? So it prevents us from being able to rely upon the value of the loss when we're picking out the value of k. The way we get around that, this also is pretty advanced, but it's something we call the elbow method, where we look for an inflection point in that loss curve. So if you were to plot out the value of the loss when k equals 1, 2, 3, and then so on until maybe like 10, you will probably see an inflection point where it goes from decreasing like this to decreasing like this. And that elbow point right there is what you will pick out as your value of k. So it's a heuristic that we built up over time, but I want to kind of just introduce you to some of the idiosyncrasies of dealing with unsupervised learning versus supervised learning. So all of these are pretty different to wrap your head around. Where's my mouse? Not find my mouse. Okay, so there it is. So let's go back to these slides. And I already did the first part of the demo. And now I want to briefly touch upon Gaussian mixture models, or GMMs. So GMMs are a modification upon k-means. And I don't want to dwell too much on the math, but I promise you that if you do end up taking CS 3780, they love this. For some reason, they really love GMMs. And I can definitely understand why, because what they do is they respect, so the influence of a centroid is a circular shape, right? So you can look at clusters that are radially distributed. But if you want to maybe capture an oval shape, what you need to do is you need to look at variance. So with k-means, we're only training for the centrality of clusters. But with the Gaussian mixture model, you add in a way to account for the variance. So what these are is actually little Gaussians that you put upon each of the clusters. And you can see that the way that they kind of form their boundaries is with this oval shape, right? So they have this oval shape outwards. And that means that they can also have a decent overlapping kind of behavior where if they get really close, you can then look at probabilities of belonging to each of the clusters. So I'm not going to dwell too much on the math, but if you are thinking of doing unsupervised learning, you should start out with the k-means model, but then you should step it up to GMMs and see if you can take advantage of the robustness, right? So this is a more complex model, right? So oftentimes that can decrease your error. In some cases, it can overfit, which is what we talked about with the bias variance trade-off. But this method as well, if you go and look, the reason we call them Gaussians is because these are basically like Gaussians that we put where we were learning for both the variance as well as the mean for each of the clusters. So it is very, very, very interesting. And the way you learn for variance, by the way, is you look at the probabilities. So the probability that a point belongs to a given cluster, rather than this like rigid assignment that we do with k-means. And in fact, Gaussian mixture models can actually fall back to k-means models if you allow them to do that rigid assignment rather than factoring for variances. So unfortunately, all that I get to say about GMMs. And before I let you guys go, because this is actually a very short lecture, I want to show you one of my favorite algorithms for unsupervised learning, which is the dbScan algorithm. So the dbScan algorithm is actually a total like graph-based algorithm. It basically makes the assumption that like, you know, every single one of these points you can think of as like a node, and then you set the specific value, but any of the points within its neighborhood are, you know, its own neighbors, right? So you can follow those edges to then like assign them or assign them to the same label. And with this method, just by starting at some random point and then following that graph, like where, you know, you're going to keep moving to the closest neighbors that you have, and then running that algorithm recursively, you can come up with very complex clusters. So let me restart this. Let's do the smiley face. So this is the smiley face, right? So can you imagine a k-means trying to learn this? Can it do it? Do you guys think that a k-means can learn this? Who thinks yes? Okay, one hand. Who thinks no? All right, someone want to volunteer why not? It's actually pretty similar to the KNN model, where the issue is that we're going to distribute out, if I have a centroid here, then that means that the influence of that centroid is radial, right? So it's everything around. So what happens here, here, and here? Those are going to be within that influence. So I can't do a good job of plucking out all of these points right here, right? Because if I have a centroid, like this cluster right here, we all agree that this like circle on the outside, which is the face of the smiley face, its centroid should be right in the middle. But then when I come up with a centroid for this like bottom part of the mouth, it's going to steal all of these points away. So it can't actually belong to the centroid. And then same issue with that right there is it's going to steal all the points from the top part, and then the other eye is also going to steal those points away. So that's the issue that we face with the centroid, is that its influence is radial. So GMMs can possibly do a little better because they account for probabilities and they form this oval shape. But at the end of the day, we need something that doesn't make structural assumptions upon our data distribution, right? So it doesn't assume that a cluster means that something is distributed out radially or in an oval shape. Instead, with the dbScan algorithm, I'm just going to run this and talk over it. So let's do this again. It starts out randomly, and then once it's exhausted all the closest neighbors, it goes down and it's running in parallel, but you could see that it's recursively just like for a given point following the 4 or 5 closest neighbors, and from each of those going to those points closest neighbors and continuing on. And here you see it actually stopped here because it wasn't able to make this jump in this gap. These were not close enough to be called neighbors. So that part though is still continuing. So we'll let that part finish, and then I'm also curious to see if it's actually able to make this jump or not. So you see that it actually wasn't able to make that jump, right? And I'll talk about why that's the case, but it will do a good job with this, I'm pretty sure. And it might, let's see what happens there. There is a decent gap. Okay, so it did do a good job there. So can someone tell me what happened here?
It was like really dependent on like what you wanted your like radius to be.
Exactly. Yeah. So there's two hyperparameters here. There's an epsilon and then there's a min points. So epsilon is the distance between, I guess, the threshold for which we call a point a neighbor. So if I'm sitting at this part right here, anything that's a circular distance of 1 away from me, you can imagine that I have an edge to, right? So that ceased to be the case here. So here it violated that epsilon value of 1, and all these were too far from these points right here, right? So if you can imagine this as a graph, they weren't joined. So I wasn't able to like assign my label to these next points. And then the same issue unfortunately happened up here, where we weren't able to assign my label to these points because they were too far. And we also set a limit on the amount of, I guess like epsilon neighbors I'm allowed to have, right? Or like the minimums. Because the other thing that dbScan can do is it can factor out noise. So if you maybe have like noise, like maybe like rather than these being, like along this, maybe there's like some like noisy points around here. You will actually factor those points out as noise and they'll go unassigned. So my point here is that this is actually a very cool algorithm because it doesn't make those structural assumptions. And when you look at the way the algorithm is written up as well, you'll find it is actually simpler in many ways. It is recursive, but it's simpler than the Gaussian mixture model, which requires you to deal with probabilities. So yeah, this is one of my favorite algorithms for unsupervised learning, which is why I wanted to show you guys. But if you do find it useful in your final projects, let me know. A couple of closing points before we wrap up today. Assignment 8 is due tonight. I did get your requests for people who reached out about extensions. I'll put those in. So if you need one, just let me know by tonight. And just also let me know how long of an extension you want. And then assignment 9 is going to be due, this says Wednesday, it's going to change to Monday. That's going to be the last coding assignment. So that's due the 21st. And after that, we have no more assignments, which means that you guys are spending all of your time that you would have dedicated towards assignments towards those final projects. And next week is our last full lecture. This lecture we call Data Science in the Real World. And we also have a deep learning workshop that we are yet to schedule. It might actually get merged alongside the Data Science in the Real World lecture. So just keep an eye on Ed for that. And if you have any questions, let me know. Thank you so much, guys.